Primitive obsession occurs when we use primitive data types instead of stronger types to represent our domain and context in our code. A special case of primitive obsession is the so-called data clump. In a data clump, primitive data types occur together as an interdependent group of parameters or fields in several places of the code. A typical example of a data clump is an address or a point, where all their components are passed individually to methods or functions or are present within a class as fields among other unrelated fields. First of all, data clumps have the same problems as the more general primitive obsession. Code is hard to scan, read and understand. The domain is not visible in the code and we have low type safety and no IDE type completion. We miss out on higher level abstractions that could act as magnets for functionality, and thus logic may be duplicated and only poorly tested. Furthermore, passing multiple primitives of the same type via functions or constructors contributes to another code smell called long parameter list. The most obvious problem here is that we may end up mixing parameters of the same type, which can lead to obscure or hard to detect bugs. However, not all long parameter lists are data clumps. The important characteristic of a data clump is that the group of primitives is interdependent. The solution to this code smell is to group the interdependent primitive data types together into an own type or class. Many IDEs are capable of directly grouping data clumps together. First, we set our cursor on the parameter list containing the data clump and open the refactoring window. Now we can choose Introduce Parameter Object. In the next window, we select which data elements belong together and decide if we want to create a new structure or use an existing one. After confirming our selection, the data clump was removed and data access is delegated to getter functions. Alternatively, we may instantiate the new type within a function or constructor and use extract parameter to replace all the primitive parameters with the new type. In cases where the data clump occurs as fields of a class, we may need to apply parallel change to get rid of it. When we have to perform a parallel change, an additional small refactoring technique called narrow change can help us speed up the replacement of read access. First, we create an indirection for the field we want to replace. Because the field is used in multiple functions, this indirection is going to be a small method that simply returns this primitive field, and replace every read access of the primitive field with a call to this function. After successfully replacing all read access to the primitive field with a call to the indirection method, we replace the primitive field within the indirection method with read access to the corresponding method of the new abstraction and run our tests. As a last step, we simply inline the indirection method again. By doing this, we now have replaced all read accesses to the primitive field with read accesses to the higher level abstraction and can continue with the parallel change refactoring. Introduce parameter object and extract parameter together with narrow change or effective refactorings to get rid of primitive obsession and data clump code smells that occur as fields or parameters. However, we have now introduced a data class that contains no functionality. This may be a code smell by itself. The idea behind object-oriented programming is to encapsulate data within a class and provide functionality in the form of public methods on that class that operate on this private data. Thus, without functionality, such a so-called anemic domain model is considered a code smell. However, there are lots of exceptions for this. For example, in functional programming, a type containing only data would not be considered a code smell. Also, DTOs or other data holding abstractions like database entries should not contain functionality either. A more important question is how we find and decouple functionality within spaghetti code that logically belongs together with these data classes or types. Once we have extracted higher level abstractions for data clumps, we often see that the spaghetti code now accesses the data of these classes, for example, through getters. If a piece of code logic accesses getters or data of an object or type repeatedly, it appears to be envious of the abstraction for the feature it provides, because it requires it to accomplish its own goals. If a class or type is envious of the feature another class or type provides, we may have the so-called feature envy code smell. In that case, we need to identify parts of the logic that actually belong to the data structure. Then we can wrap and extract the functionality belonging to the data structure as an own function. And move it closer to that structure. As you may recall from code smells about complicated conditional expressions and deeply nested control flow, when we extract parts of logic as methods or functions, their parameters may be data clumps or data classes. In many cases, these parameters are great candidates to move the functions to. With feature envy, we now see how in general, extracting functions as solutions for complicated conditional expressions and deeply nested control flow can work together with wrapping data in own classes or types as solutions for primitive obsession and data clumps, and finally grouping data and functionality closer together as solutions to data classes and feature envy code smells. This procedure of wrapping and extracting data and functionality into own abstractions and to move them closer together is one of the most powerful tools to entangle spaghetti code towards a maintainable, future-proof software design. We will practice this procedure we could call emerging software design even more in the upcoming final part of the course. As a last note, however, there are several pitfalls that are out of the scope of this video. For example, that the extracted functionality should never break any architectural pattern like layering. These topics are vital for decoupled, cohesive software design, but require the introduction of a lot of additional concepts. I will provide more sources for these topics in the learning path.